Hi everyone, a big welcome to you all. My name is Venki Nagapudi. I'm a principal product manager with the Elastic Block Store team, and I'm here today with Prithvi Karamanchi from Netflix. And together we are going to go over how you can use EBS to run your high performance single instance and clustered applications. We have a fairly packed agenda today. I'm going to talk about how you can optimize your single instance database. Then I'm going to touch upon how you can add reliability hooks so that you can get to deploying high availability and disaster recovery for your databases. And then I'll briefly touch upon how you can use EBS multi-attach to get your clustered file systems going. And then I'll hand over to Prithvi so that he can go over a very interesting use case for EBS multi-attach for cache swarming of memcached at Netflix. So let's dive into it. Let me first start with a brief introduction of the workloads that run on EBS. So we have millions of customers who run a variety of applications and workloads on EBS. Some of them, such as the database workloads, need really high IOPS and low latency, whereas there are some applications that need higher bandwidth. And these are the ones that have analytics, they're about file systems and media and entertainment. Now, we are seeing in recent times that there is an increase in the amount of performance needs that our customers have as they move more and more of their enterprise applications from their on-prem to the cloud. So if you are a database administrator or a storage admin, you will likely have a need for hundreds of thousands of IOPS when you're running an Oracle database or a SQL Server or an SAP HANA. You might also need multiple gigabytes per second of bandwidth. And you have a need for both single instance databases, single instance applications, and also the need to optimize clustered applications. You might want to start small using the fewest number of CPU cores so that you can optimize your license costs. At the same time, you want the ability to scale your compute and your storage so that you can get to higher performance and higher capacity as your needs grow, such as when you want to add more users for your database. So, and you want to be able to do all of this while you ensure reliability and data protection for your applications. And this would mean that you need strategies for high availability and disaster recovery. So how do you go about doing all of this? That's the focus of our presentation. So we'll do this in a phased manner. We'll start with single instance database and how you can optimize that. And then we'll add a few hooks for reliability, and I will show you how to do backup, HA, and DR. And as I mentioned, I'll briefly touch upon how you can optimize your clustered file systems with multi-attach, and then I'll hand over to Prithvi for the Netflix use case. So let's first start with the single instance databases. So let's say here is the scenario we are looking at. You have a SQL Server instance that is running on a SAN array in your on-prem deployment, and it's able to give you 250K IOPS and 7.5 gigabyte per second. So you have a number of questions, including, does EBS offer anything that will meet this kind of a performance need? And if it does, then what are the kind of volumes I need to use and how many of these volumes? What are the instances that I should use out of the tens of instances that I have to choose from the EC2 instance list? Then how do I start small? And as my needs grow, how do I increase my capacity and performance? What does the optimal setup look like in terms of performance? And how do I achieve all of this without breaking the bank, right? And let's touch upon all of these in that order. And we'll start with the volumes to begin with and the instances. So for your high performance database needs, while you have a choice of both HDD backed volumes and SSD backed volumes, we suggest that you look into using SSD backed volumes because those are the ones that give you the highest performance and the highest consistency of performance as well. So you have a couple of options to choose from. There is the general purpose IOPS, general purpose volumes that provide up to 16K IOPS and 16 terabyte of capacity. You can stripe multiples of these volumes to get to the performance and capacity you need. You also have a choice of provisioned IOPS, and provisioned IOPS give you much higher performance at 64K IOPS per volume and 1 gigabyte per second of bandwidth. But importantly, you get a high level of consistency of performance, especially for your latency. And low latency and consistently low latency is critical for your database applications. So you can get that with the provision IOPS volumes. And importantly, the new volume type that we introduced, the IO2 provision IOPS volume, is able to give you 5 nines of durability in addition to 5 nines of availability. And so if you have mission critical and business critical applications that use databases, then we suggest that you use the IO2 volumes. So in terms of your instances, well, there are tens of instances available to choose from. We recommend that you use the R5 or the R5B EC2 instance, which has optimization for EBS bandwidth. Now, R5B is a new instance we just introduced. It provides you with 260K IOPS and 7.5 gigabyte per second. And importantly, it'll give you the consistently low latency that you need. And that's because we have what is called the Scalable Reliable Datagram, or the SRD protocol, that ensures that the latency between the EC2 instance and the attached EBS volumes are the lowest possible and consistently low. So for your SQL Server database, we certainly suggest that you use the R5B instance. Now that we have narrowed down the instances and the volumes, let's take a look at how you'd be able to scale your SQL Server for your different performance needs. Let's say you want to start small with 40K IOPS. While you have a choice of using R5 or R5B, we suggest that you use R5B because you can get by with 1/3 the number of cores. And so if your database is more IO heavy rather than compute heavy, that means that you're going to save 66% in terms of license costs. And let's say your performance needs are more than the order of 160K IOPS. Well, you cannot use R5 anymore because it tops out at 80K IOPS. Instead, you use R5B. And you could use either the general purpose volumes or the provision IOPS volumes. But in general, we suggest that you use the IO2 volumes because IO2 brings 100x higher durability than the general purpose volumes. And a stripe of IO2 volumes is going to be smaller than a stripe of general purpose volumes. And it's going to get you to much higher durability than general purpose volumes. So we suggest that you use IO2 for your data volumes as much as possible. So let's take a look at how the optimal solution looks like for your high performance SQL Server. We do think it should use the R5B. And R5B today supports GP2 and IO1 volumes. And soon enough, it's going to support IO2 as well. For your volumes, you're going to split them up as data, log, and temp. For your data volumes, you could either use the general purpose volumes or provision IOPS volumes. But as I mentioned, it might be useful to use the IO2 volumes because of the higher durability. And for your log volumes, which are very critical for your database performance, and that's because the log volumes need really high write bandwidth as well as consistency of latency. We suggest that you use the provision IOPS volumes, right? And those deliver the best consistency of latency. And if not, use instance store there if you can. So with this being your optimal configuration, how does it all look like when we run some performance benchmarks? Let's take a look at that. So what we did was we ran TPCC benchmarks against both R5 and R5B. Now TPCC happens to be a fairly simple and useful tool to evaluate the performance of transactional databases. So we created a SQL Server database using 4 IO1 volumes. We created 30,000 warehouses out of them. And then we ran what is called the new orders per minute, or the NOPM metric test. And this is a platform independent metric that you can use to gauge how well your database is doing. So we compared the performance of R5 and R5B for different IOPS numbers. And it's very easy to dial up the IOPS using elastic volumes. And so we used a single set of 4 volumes and we dialed up the IOPS, as you can see. And what we were able to achieve was that R5B gets you to nearly 3x or 3.2x higher performance than R5, making it the instance of choice for your SQL Server applications. So to summarize, for your high performance single instance SQL Server, do use R5B and do use IO2 whenever the support for IO2 is available with R5B, which should be pretty soon. And by doing that, you'll save about 66% in terms of license costs, especially for your IO-heavy transactional use cases. So with that, let's take a look at now how you can achieve reliability for your database applications. If your database is a part of a business critical or a mission critical application, which needs to be always on so that you don't lose business continuity, then you need to have a second copy of your database running either in a remote availability zone or a different region, right? And the kind of parameters that you need to take into account when you design your high availability and disaster recovery are two things. These are called, the first one is the recovery point objective, or the RPO, which is really the time interval between two database volume backups. And that is a measure of how much of a data loss you can suffer before it starts impacting the business continuity. The second one is the recovery time objective, or the RTO, which is the amount of time you have available to stand up your disaster recovery instance in a remote node in case the primary database goes down for whatever reason, right? And your RPOs and RTOs can be in the order of seconds, or they can be in the order of minutes or hours. And based on your application business continuity needs, you have several choices of infrastructure as well that EBS provides. The first one that I want to talk about is EBS snapshots. EBS snapshots are great if your RTO and RPO requirements are in the order of a few hours. EBS snapshots are point-in-time backups of your volumes. And the good part about them is they're incremental in nature, so they're very cost-effective as well. And with snapshots, you actually do get application consistency as well, because you are able to integrate EBS snapshots with Windows VSS, and you can get to application consistent SQL Server database snapshots. What you do is every few hours take snapshots, and then you can restore them either in a remote availability zone or a remote region. And you have a couple of different options to restore your database. One is standard restore. The second is what we call the fast snapshot restore, which provides a terabyte an hour in terms of performance. And with that, you should be able to pretty much bring up your databases within a few hours in the case of a disaster. So simple use case for EBS snapshot. So we believe that this is a very cost-effective means to back up and restore your SQL Server databases. We also provide a number of inbuilt SQL Server options in case your business continuity cannot tolerate a long RPO and RTO. In this case, you need to use the built-in tools that are available with SQL Server, which deliver close to zero RPO and RTO. These are what are called the always-on availability groups, and we support them. So the thing to watch out here is that your secondary infrastructure is always going to be up and running, so you'll incur costs there, as well as you'll incur the costs for the standard licenses or enterprise licenses as the need be. But you do also have a third option available. There's a cloud Endure solution that AWS offers, which uses EBS snapshots and volumes underneath. So if your application is able to tolerate RPOs in the order of a few seconds or even sub-second, right? And if your RTOs can be in the order of minutes, then you can use Cloud Endure successfully. The good part about Cloud Endure is that you don't need to have your infrastructure up and running, and also you won't need to use the licenses unless there is a disaster. So with that, right, you will be able to optimize your DR cost for SQL Server database using the Cloud Endure solution. Now, let me move over to the second part of what we want to discuss today, which is all about clustered applications and how to achieve them. So in February of 2020, we introduced a feature called EBS Multiattach. EBS Multiattach is a way to have your provision IOPS volumes share the performance across multiple EC2 instances. So in this case, let's say you have a PIOPS IO1 volume with 64K IOPS, then you can share that performance with up to 16 EC2 instances. And if you want more bandwidth, more performance than that, what you can do is take a stripe of these volumes and then share the stripe across multiple EC2 instances. And you can then enable clustered file systems, clustered databases, and your own custom applications as well. But the caveat here is that you need to have I/O fencing available either in the file system or in your application. That's because the multi-attach feature doesn't support I/O fencing at this point in time. It's a feature that we are going to introduce in the next few months, so stay tuned for that. But in the meanwhile, we do see a lot of customers using EBS multi-attach for running clustered file systems like GFS2, which has built-in I/O fencing, or they can run custom applications which bring their own I/O fencing as well. So let's touch upon the first part. Let's say you wanted to create a clustered file system. Here is an example of a GFS2 file system. What we did was we created a 3-node GFS2 file system with R5.24XL nodes. And we pretty much saw the maximum performance that we could derive out of these 3 nodes, which was 240K IOPS for 16 kilobyte IOs. We also saw 7 gigabyte per second of bandwidth for sequential reads and writes. So you can use multi-attach with clustered file systems. And we are very excited because when you get to R5B, you're able to get to 30 or 40 gigabyte per second of bandwidth out of a clustered file system, and that will enable a whole variety of applications for you. While you could use a clustered file system underneath for your high-performance application needs, you don't really need one. So we are now going to talk about how Netflix used a non-clustered, like a simple file system like XFS, and managed to get Memcached optimized using the EBS multi-attach. Thank you, and over to Prithvi now.
All right. Hey, good morning, folks. This is Prithvi. I'm a senior software engineer at Netflix. Today we'll be talking about cache warming using EBS Multiattach and its relevancy at Netflix. So the agenda of this meeting will be briefly touching upon what is the cache that is involved, what is cache warming activity, and what is the scale at which this service gets operated, and what are the problems with the V 1.0 architecture that we have currently in production, and then we'll be presenting you with a new architecture which leverages multi-attach EBS. Okay, so let's talk about the cache that is involved. So we're talking about EV cache, which is both client and server-side component of which makes Memcached distributed in nature, and it is optimized for running on AWS, and it is tuned for running all the Netflix use cases. It has a lot of features that are built in, which enables features like replication, and it is highly resilient. Also, it is topology aware. Also, there are a lot of features that we could enable or disable on the fly, which make it very powerful. And let's talk about the two variants of Memcached that we have. So we know that Memcached is a key value store, but there is another variant of it where the keys themselves are stored in memory, but the values go to the disk. And we have a large footprint of use cases which use external storage. That means there is a big amount of that means the size of all these caching servers, it is significantly high, and we'll see why that is relevant for cache warming in a bit. So what services touch EV cache here at Netflix? EV cache, let me say it's a tier 1 service, tier 1 microservice here at Netflix, and without EV cache, all the clients, they are expected to go and hit bombard the database servers, and database servers are going to crash. So all the microservices, they hit EV cache, and then it sort of guards all the client requests from not landing on the databases. And some of the well-known user-facing services include sign up, personalization, then playback, searching, then we have viewing history, And then there is algorithm and machine learning training, for which EV cache is very widely used. Um, okay. Let's talk about the EV cache footprint here at Netflix. We have petabytes of cache data that is stored on EV cache, and we have trillions of items that get stored here. And at any given point, we're talking about hundreds of millions of operations that the EV cache servers are handling. All of this is distributed on hundreds of distinct clusters, and each cluster has a different access pattern. And all of these are again distributed on tens of thousands of EC2 instances. And this is all spread across multiple regions. And we sort of replicate most of our caching data across the regions just to protect us against any region failovers. Let's talk about what is cache swarming and then why is it relevant, just to set context on this use case. So cache swarming is the act of migrating the data from the old clusters to the new clusters. And from time to time, there are some unplanned uh, maintenance issues, and sometimes there are planned activities, scaling events or scaling activities that happen. And the most recent scaling activity that we had to do here at Netflix was during COVID time. There was a sudden surge or spike in Netflix consumption, thereby pushing all our services to their maximum capacities. So we had to quickly upgrade or scale up all our services to make sure there is no disruption to the end user. And since EV cache is sort of fronting most of the databases and all lot of microservices, we have to do it fairly quick. The other times when we have to do new deployments is there could be critical kernel fixes that get rolled out, and we have to migrate we have to basically upgrade all the existing clusters to the newer versions of kernels and so on and so forth. Also, from time to time, we do horizontal scaling of our instances. So we are forced to move off one instance type to a different instance type. The thing with the nature of this caching data is the TTLs on these are not small. They sometimes range from few hours to few weeks. So we pretty much treat this data like a fairly long-lived data and not really like your typical short-lived caches. So the new deployments that come up, they can't take the read traffic right away because they are bound to get a lot of cache misses. So we have to make sure that the new deployments have all the data from the old clusters so that they can start serving the reads. So what are the design goals of the cache swarmer architecture, cache swarmer that we have in mind? So the first thing is we wanted to have least to no disruption to the existing EV cache clients. We also wanted to minimize the resource consumption on the EV cache nodes when the cache swarming activity is happening, especially memory, because memory is a very scarce resource for us on the caching servers. And another important design goal for us is we want to accelerate the warm-up time to as quick as possible. Also, we should be agnostic of whether the warming activity is happening during a peak hour or a non-peak hour. So with these design goals, we have this cache swarmer architecture, which is basically V 1.0 architecture. Let's quickly go through the entire workflow. So we have cache swarmer controller, which serves as the orchestrator, and it orchestrates the entire cache swarming activity end to end. So the first thing that it does is it creates an SQS queue, dedicated SQS queue for a particular warming event. Then it will instruct the memcached server nodes to say, hey, why don't you start dumping your data? And the data that gets dumped, it will be split into chunks and then it gets uploaded to S3. Also, the location of the chunk in S3 will be sent as a message to Amazon SQS queue that we have created in step 1. And on the cache, and then cache from a controller is going to instruct cache populator, which is another microservice, and its sole responsibility is to read the contents or the chunk information from S3 and then basically cook up the memcached requests and then add them to the destination clusters. So this architecture, it has worked really great for us for the past 2 years. But in the past 2 years, the EV cache as a service also has grown significantly in terms of the data footprint. So we started noticing we started hitting some bottlenecks with the existing warmer architecture, right? The first one is we started to see some impact on the production traffic, thereby increasing the latencies. Also, the S3 network bandwidth, from time to time, it was contending with the client traffic. So that was a side effect of uploading to S3. Also, the dumper that we saw in the little diagram earlier, it is based on JVM. So whenever there is warming activity happening, if the GC doesn't happen fast enough, we used to see occasional JVM crashes with out-of-memory errors. So since these were the limitations, we started again looking at this problem from a different perspective. And luckily, around the same time, EBS has rolled out this new feature called multi-attach EBS, where you could attach the same EBS volume to multiple instances. So it sounded really great on paper because EBS has a dedicated storage bandwidth from the instances. That means the application traffic and the EBS I/O, they are not contending for the network. At the same time, we thought we could potentially pipeline reads and writes at the same time. Thereby, we could leverage the full potential of multi-attach EBS. So with these things in mind, we went back, we came up with a new architecture. So if you see this diagram, it's very similar to what we saw earlier. But the S3 and SQS component, they have been completely removed from the architecture. Instead, we replaced it with EBS. And the new architecture goes like this. The cache from a controller, which is the orchestrator, it provisions the EBS volumes and it will attach, it will create one EBS volume per source instance, and it will attach to the source instance and also to the cache populator instance. And the controller will instruct the EV cache server instances to say, hey, go ahead and dump your data. And the dumper will start writing to the EBS. And in parallel, the warmer also instructs the populator service to say, hey, go and start reading the chunk information from the EBS volume. And it will start reading those data. And again, it will cook up the requests to be sent to the server side, and cache populator does exactly that. And in this diagram, if you see, we have also introduced a new component for the dumping, which is native cache dumper, which is the dumping activity that was done by JVM. It's been completely written in C++ to be memory efficient, and it has worked again phenomenally great for us. So how does the EBS, multi-attach EBS really, how did we leverage it under the hood, right? We had the option to use clustered file systems, but we decided not to bring in one more layer of complexity to our architecture. So we decided to stick with the standard file system XFS. On the source side, we have mounted it with a WSync option, which will make sure that any writes that you're writing on the file system, they get persisted to the underlying underlying block device. And we also make sure that we run fsync on files and directories. That will also make sure any metadata, any file system metadata at directory level, all of that gets persisted. On the destination side, because it's a EBS volume, it will only fetch the point in time data. It doesn't know about any changes that are happening underneath it. So we had to do a mount and unmount in a loop. That way, every time you do a mount after some time, you're essentially going to get a new set of files visible on your mount point. And on the destination side, the cache warmer uh, uh, service can read this chunk information and then write to the destination clusters. And just to be on the safe side, we also compute the checksum of the data chunk files that we write to the multi-attach EBS volume. And on the destination side, before really reading it, we recompute the checksum and validate that everything looks good before writing to the destination. So, what does this prove, right? So this slide sort of hits the nail on the coffin for us. With the existing architecture, to warm up a petabyte of data, which is one of our largest clusters that we have, it used to take more than 40 hours, and there were like a lot of hand-holding from engineers that we had to do from time to time. And it was not really reliable. And this was a direction where we are going with that old architecture. And at that time, we experimented with multi-attach EBS and we deployed it. It is running in production as of today. And we were able to warm up that same cluster under 6 to 9 hours, which is a huge win for us. And performance is one aspect of it. The other thing is the quality of warm-up data. With the existing or the V1.0 architecture, we saw a lot of cache misses because not all the data got warmed up. Whereas with the new architecture, it's pretty much close to 99.99% reliable. So the quality of warm-up data has also been significantly good. So what are the takeaways for us? I would say EV Cache team, and particularly at Netflix, we have been extremely happy in leveraging multi-attach EBS, and we look forward to leveraging this for a lot of other use cases within EV Cache. Are all the limitations addressed? I would say yes. All the limitations, whatever we had with the existing architecture, they have been addressed. I would like to acknowledge the entire EV Cache team here at Netflix, especially Sailesh, Shashi, and Taranga for their contributions. And a huge round of applause to Nimisha and Mark from AWS for their help along the way. Thank you, folks.